So I'm going to encode effective addresses that include displacements this time. So that's basically going to include all of these 8-bit displacements here, all these 32-bit displacements, and this special case which in 64-bit mode is actually RIP-relative. I'm going to skip these SIB tests for now. I'll deal with that a bit later. But I'll be doing tests for RIP-relative addressing and the registers plus some displacement. So we'll just start by generating some tests with NASM again. Let's just separate these out a bit. So if we do plus OX7F, this will be an 8-bit displacement. Then if we do a copy of all these and add FF, these will be the 32-bit displacements. And then we'll add some RIP-relative tests as well. So the NASM syntax for that is rel $ plus some offset. And this displacement is always 32 bits. Okay, so let's just maybe what I'll do here is also include the opposite tests as well. So we'll just copy all of these and go down to the end of the file. We'll take all these destinations and make them sources. Okay, so let's assemble this. And then disassemble. Okay, so let's take all these as our test cases. So we've got MOV to mem plus disp from reg here. We'll have to fix this formatting. And let's look for whether we've got the break to the opposite direction. So here we've got MOV reg from mem plus disp. Okay, so let's just change these. This relative syntax has been changed by the NASM disassembler. So we'll just change this back to $ plus OX7FF, FFFF, and then we'll change all these to be uppercase as well, just to be consistent. Okay, we'll remove this offset. This is the expectation. This is the instruction. Okay, so let's just fill this out. I think I can basically take from these tests up here. So we'll do the mem to reg ones, or the reg to mem ones first. So this is all of the bytes operands, which I can do on all of these except for the top one because that's a RIP-relative. So we'll just take these down here. And then we'll take from the word ones here. So these ones will go, so this one is RIP-relative, then we'll skip that one and we'll go down to here, so that's 7 of them. Then there's another 7 down here. Skip the RIP-relative one, we'll go and put these ones in here and here. And do the same for these keyword ones as well. So I just need to change these to keyword. These ones change to dword. Then I just need to fill in these RIP-relative ones. So RIP-relative, I'm basically going to have a new operand called IP. And this will be from AX. So this one down here is keyword. This one is dword. And this one up here is word. Then for all of these M these M calls, we need to add a displacement for the test. So we'll just go and get all these ones. So this will be D with some value. So the value here is basically OX something. So let's go to D and put those in there. And then these ones where we've swapped the operands around, I can just take all of these test cases now and just swap them. And we'll put the source on the other side. Okay, that should be all of the tests done. We'll need to create the new operand. So this one's going to be IP, which is an operand. It's a register. And we'll have another flag called rel to mark it as a relative, so RIP-relative. This has the same value as BP, which is 5. So we need the rel flag as well. And let's just try and run these tests. Okay, so we get lots of failing tests. Okay, that's good. So now we just need to go to the generator and actually implement this. So in the generator, we need to decide more on what mod is going to be. That's going to be basically most of what I need to do here. So let's just redefine mod here. We'll say mod is address direct by default, because we've got a switch case here, but we're only using one case, and the other one is default. So we'll just only change it if it's mem. Then we just assume it's indirect. So here we'll say we'll do something. So if Rm is displaced, and it's not relative, then we want to change the mod. So if Rm is disp and it's not relative, because if it is relative, we don't want to change the mod. We want to leave it as 0, 0. Then we need to decide which one it will be. Is it going to be disp8 or disp32? So we'll basically just take the displacement from Rm and we'll say that if disp is equal to itself after it's been truncated and then expanded again, that means that it would fit into an 8-bit displacement. Otherwise, we'll fall back to 32-bit. Then we come through to here and we say if Rm is membp. So if it is membp, that means that it's going to be either BP or R13. And in this case, so if we've got membp, if we're using BP and we want to add a 32-bit displacement, we need to make sure that it doesn't get changed from that. So this is a special case only. This is a special case only for mod 00 here. So if we're using BP in this case, that's actually going to be RIP-relative. So if we actually want to use BP, that's when we do the special case to come up to this disp8 here. So we only want to change the mod in the case that mod is already address indirect. Then we want to bump it up to 8 bits because we need to add a 0-bit displacement. So then at the end here, we're already adding the displacement from the BP exception there, but here we need to add either 8-bit or 32-bit. So this will be disp is equal to this, and we should switch on mod. So in the case that it's address indirect disp8, that's what we're already doing. In the case that we've got a 32-bit displacement, then maybe what we could just do is text equals binary.little-endian, because they're little-endian CPUs. We'll say append uint32 onto gtext, and we'll convert to uint32 the value of disp. And we're also going to have a potential disp32 in the normal indirect case, but this is only if it's RIP-relative. If it's not RIP-relative, then we can ignore it. So basically we'll have another case here, which is just indirect. And in this case, we want to do the same little-endian 32-bit displacement, but only if Rm is rel. So we've got some problems with RIP-relative, so it's only RIP-relative that isn't working. So basically what is going on here is that we've got the correct opcode, we've got the correct ModRM. So this one is 8805. So 05 is 0000 1, oh no, 01 01. So this mod RM here, this mod here is basically the mem, just normal indirect, no displacement. Then we've got the reg field, so this is 0, which means it's AX. So that's where we're getting AL from for the reg. Then we've got RM, which here is 5, which would normally be BP, but in the case of 00 with no displacement, this is actually the RIP-relative. So that's RIP-relative. So this 8805 is correct. Then we've got the displacement, where it's little-endian, so it's been switched around in the actual machine code. But the difference here is that this has F9 down here, whereas we've got FF. And the problem is that the RIP-relative is actually relative to the current instruction pointer. And so while we're executing an instruction, the instruction pointer has already moved to the start of the next instruction. So this displacement actually needs to be the displacement minus the length of the current instruction, because we're just assuming that if it was directly encoded as the value that we actually typed, that would be assuming that the IP is at the start of the instruction. But it's not, it's at the end, so we need to minus this length here. So we need to keep track of the length. So we start appending to text over here, so this is where we'll keep the pos. We'll say pos is the len g text. And then if we're doing RIP-relative, then we'll say, let's call it n. This will be an int32. Int32 of len g dot text minus position. So this is the length of the instruction that we've encoded so far. But then we're going to have 4 extra bytes, so we need to plus 4 to this. So we're going to minus n from the disp. And that's all passing. So that's memory access using a register as the base plus some displacement. So that's 8 bits and 32 bits working. And we're doing RIP-relative as well. And we're doing that in both directions. So we're doing, we're doing R and RM, and we're doing RM and R.